I'm delighted now to announce it at very short notice and not in the program, an incredibly special guest that we have with us today. Now, he's not just been working in wave energy for 40 years, not 14. He's not just a leading authority, he is a giant in the wave energy field. A professor and champion at Southampton University, a recipient of the Royal Society Medal for Particle Physics, he's here as an inventor today to tell us about a new way he's discovered for capturing wave energy, that is, producing electricity from the sea. A couple of years ago, he organised a conference which produced this book on wave energy, and I've had a look through it and I don't understand it one bit. I'm not sure that studying any harder in mathematics when I was in high school would have helped at all, but here to tell us all about it in detail is Professor Frances Farley. I welcome you to the stage, Professor.
Good afternoon, good morning, ladies and gentlemen. What? Get closer? Yes. People often say to me, could you get closer? And I look forward to that. Now we want to move forward. Yes, I'm going to speak about energy from the waves of the sea. The sun does not shine at night. Solar energy no good at night, and the wind doesn't always blow. But the waves in the sea are always there, and there's much more energy in the sea, in the waves, than there is in the tides. What happened? Nothing happens. Yes. Okay. That's where we were. Can we go forward? No. Do I press it again? What? Yes. So we want to plug into the wave. Many people have dreamt of wave energy, and here's the guy dreaming, but all these things have fallen to pieces because they're too weak. And this is what normally happens. It may take a year or two. Here are two things on the left that were supposed to be the front runners in the UK, Pelamis and Oyster, but in spring this year they both went bankrupt, folded their bags. The wave bulb is another thing that went out of action many years ago, some years ago. They're too complicated and too many moving parts. Doesn't work. Do I have to point this somewhere? This one. Now I'm going to talk about a bag underwater. This is a bag underwater full of air, compressed air, and there's a float at the top and a ballast underneath, neutrally buoyant. But it turns out, which is what I discovered, that the combination of the ballast and the bag resonates with the waves. You'll see this in a minute. The waves will come along from the left. There's a conical float on top. You'll see the waves at the top, and you'll see the bag moving. How do we turn it on? Yes, no. This is chaos. What do I do? Can someone help me? This is not the message. We need a bit of help too. I want to move forward, yes. Let's start again. Do I say move forward? The point is, yes, move forward. No, it's too fast. Go back. No, see if you can play that. That's the forward. It should play. It's a video. In my computer it works, but this computer doesn't. No, well, it won't run. Never mind. But this is very striking. You see the bag moving up and down, resonating with the waves. Go on to the next, please. Next slide. Yes, so we have an underwater bag full of air, ballasted, and as it goes up and down, the air is pumped through this. Next, please. Can I have the thing? Next, please. Next. So the air is pumped from V1 into V2 via a turbine, generate electricity. There are no moving parts, no hinges, no joints, nothing needs lubrication, nothing can break. Next, please. Yes. Now there are two resonators, the float and the next one. Yes, and you get a double peaked response. Press the next. You get a double peaked response, wide band. The power output is vertical there, and the wave period horizontal. It goes from, say, 5 to 11 seconds, a very wide band response. Next one. Yes. Next one. So these are some other, this is all computer calculations. But in large waves, you get less power out. That's the green curve, because the bag has limited volume, and that means the turbine is protected. Next one. Yes, this is tests in Plymouth University about a year and a half ago, and we see the power output reaching the theoretical curve and the two peaks that I predicted, and very wide band response. This is a very small waves, 1.4 second waves. Next, please. Yes, this is how it would look. A cone, say 20 meters in diameter at the waterline, the bag underneath, and the second volume on top, and the turbine is there. It's turned, it has a horizontal axis, so it doesn't generate gyroscopic forces when the float pitches. Next one. Yes, this is another example where we've increased the mass of the float by adding a tank of water. Seawater, very cheap. You can always add water. It doesn't change the buoyancy, but it does increase the inertia and lengthens the period. Next one. So, survival. If you deflate the bag, it goes completely flaccid. The ballast just hangs down. It doesn't move. It doesn't pump any air. So, in large waves, you protect the turbine. Yes, thank you. Large waves protect the turbine. In a storm, the whole system is sealed. So you can sink it. We don't connect to the air, so no water can get in. You sink it, say, 50 meters. There are no waves at depth, so the system is protected. When the storm passed, you bring it up again. Here's some technical stuff. Next one. The pull point is one of these machines would generate about 100,000 euros worth of electricity to the consumer. A slightly better version, next, press again, 200,000 euros worth of electricity. Now, what is the cost of the machine? This has to be worked out. You need detailed engineering studies. Next one, please. So, this is the summary. Don't read it. Go back, please. Go back, please. Forward. Forward, please. Yes. Survival. Forward again. Forward, forward. 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 You're going back. Forward. Forward. We need to get to the summary, and then you won't see me anymore. Conclusions. Why Yeah, I can't read it. Stop, don't press anymore. In Morocco, there's a huge amount of wave energy in the sea, 70 gigawatts roughly, and that is enough, much more than the total installed capacity in the UK. And Morocco is a leader in alternative energy, wind, photovoltaic, but you need to supplement with wave power. And with this wave power of this very long coast, 3,600 kilometers they tell me, you can get a lot of wave power and supply other countries in Africa. So this is why we should do it now, because we have a very cheap solution which will survive because there are no moving parts. And this is what we want to do. So please, thank you very much.